welcome to another session on MP3672. Apologies, I nearly forgot what the module code was then. So what we've done so far on Comsol is we just looked at validation and the typical procedure of that you can use to do that. What I thought we would do today is do a little bit more of conventional things. So for example, in this case we're going to do the good old Dogbone design. And then what we'll do is we'll calculate the maximum stress, and from that we use that as a guide to give us a rough estimate as to where we are when we come to the full simulation of the part. This, again, for me personally, this is one of the very good, big, strong points of Comsol. I personally prefer it when it does these types of things. I love the idea of being able to have everything all self-contained. We've got a calculation which has been committed, and then you can refer to that when needs be. So what we'll do first is we'll go to Model Wizard, and I'm gonna create the 3D space straight out, right? Because I'm doing a 3D Dogbone. And then what I'll do is I'm gonna incorporate, well, I mean these are up here because these are what I was last using, but I'll follow correct procedure. I'll go down to Structural Mechanics, I'll go to Solid Mechanics, and then I'll go to Add. Any minute now. So it comes in, gives me my typical field, my displacement fields, my displacement components, to just let me know what I'm operating to. So now I'll go to Study. And in this study we're going to do a static study. So basically we're going to pull this thing apart and see what type of maximum stress it gives us. So I'm going to do a stationary study. I'm going to add that. I'll double click that because I'm always never sure. So I'm just going to double click it just to be sure, and we're in. So this is our full structure at the minute. So what I'll do first is I'll go up here and I'm just going to give this a title. So I'll call this Dogbone. So I'm onto the Dogbone test. I'm going to come back to this later. Of course, this is me who's done this. And I'll come back and populate this a bit more afterwards, because I like to have a thumbnail on there as well. So when you are going to open it up, it gives you a little bit of a this is what it's doing. What I'd like to do as well is, I think once we've done this, I'd like to also open this up in MATLAB. So what we'll do is we'll complete this, and then we'll turn the MATLAB conversion into another video for you guys to follow. So I'm going to go Parameters. Now with this, I'm going to set myself up with some variable names. Now I'm going to go, I mean some know this as a dumbbell. You can know it as whatever you particularly refer. So I'm going to TW, I'm going to call this thickness to weight. So let's just say it's the dumbbell design. What I'll do is start off with my example. So I've got 10. I say my example because this you will find in the notes of what it is that I'm doing. So I'm going to go 10. Now don't forget, when you're putting in your units, square brackets. There is a term for square brackets, but I forget what it is. So I'm going to go square bracket, millimeter, and close. If I tab, the value should be seen in meters. If you don't like that, we can change that in, let me just go, oh, it's not all defined yet. Can't change that just yet, but we will do. And here I'm just going to call this thickness to weight. So now I'm going to go LW, which is the length of the weight. 10 millimeters. The reason I'm doing this is we're actually going to use these variables to allow us to model exactly what the dumbbell does in its particular actions. So when we draw it apart, if we do want to change variables, it's amazing. We've got variables that are controlling it. We've got the dimensions predefined within it. If we want to do parametric studies, dead easy. It's very, very straightforward. And I would like to actually examine the use of parametric studies. So I'm going to go LG, we'll call this grip length, or length grip, or whatever you want to call it. So I'll go 20, open square brackets, go millimeters, and then we go tab, and then we'll just say grip length. Then we go, I've not chosen the best names here to be fair, so I'll call this weight to grip width, or basically I'm going to call this WG. The worst thing is once I get a thought in my mind of what it, now this is, if you will, if you imagine your dumbbell weights, this is the recess of where the handle is. That is because, I mean, I'm choosing these because this design is actually on the ANSYS notes that I gave you, but I thought it might be nice to just, I've just put that in wrong, it might be nice just to do this as an example, to really show the differences. Again, I'm just trying to point out this is not a dig at any particular softwares of saying this is better, this is not. This is not about that. This is to allow you to really make a decision for yourself of what you prefer. So again, ANSYS is a phenomenal piece of software, but this is not a dig at ANSYS. So with that now, I'm going to do the longitudinal loading, which is what we're going to be using to actually draw this part apart. So I'm going to call this LF. I could call it LL, but I call it LF for longitudinal force. And we're going to go 20,000 newtons, I think it was. Don't forget we're in newtons, so we're going to go square brackets, uppercase N, square brackets, and now we're in for what we got there. So this is longitudinal loading, so long... And then finally, what we want to do now is calculate the maximum stress. We've got everything that's there. We know pretty much everything that we need. So what I'll do is I'm going to say MS, which is going to become my target value variable. So I'm going to say 4 by LF, whoops, multiply by LF, close that, all over, TW, to the power of 2, closed, multiplied by pi. So we open it and close it. Now you'll notice that I've got uneven brackets. That's because I forgot to add that one in. So if I tab that in, so we've got a target value to be aiming for. So now what we need to do is, now we've got this nice target value to go for, let's move this on a little bit. So I'm just going to bring this up. Let's move this on a little bit. What I now want to do is I really want to start playing around with what this is going to do. So first thing I need to do is I need to start bringing in some geometry. Now if I click on geometry, that's what it does. You kind of go, brilliant, spot on. So what we're actually after now though is we want to start making our geometry so we can test against exactly what it is that we're talking about. So first things first, I need a work plane. This, like anybody who's proficient to CAD, you will know that within a plane it is a two-dimensional representation of a point in space that we can operate with, X, Y, Y, Z, whatever it is that you know, your reference is. What I'm going to need to do though is I want to place geometry. So now what we're going to do is we're going to model each line representation. Then once we've created each line representation, we're going to create a 360-degree rotation to give us the dumbbell design. Because as we know, if you look at half of that profile and you look at how it's been executed, you can see that the best way to do it is side profile and revolve around it. We will use that to our advantage. By using this, it does minimize the computational need of the system and makes it far more efficient. So let's move into the first piece. Now, I mean, if anybody sees, you will get a lot of people who have different preferences as to how they would produce this. So what I normally do is I like to use segments. Now you'll see why. I mean, again, if you come away from this and say, oh, well, you could do that instead, that's great. And I'm just showing you a particular method that I normally use. Now you see here it's at vertex. You can locate this to be wherever you want it to be, but as I said, we're going to do this through coordinates based. So if I change my variables, the dumbbell will change in resolution to what it is that I'm doing. So I'm going to change this to coordinates and change this to coordinates. Anybody who's proficient to API or CAD all round, you'll know that XY and XY coordinates align is simply 2 points that are connected. So you're asked to place the first coordinate, then asked to place the second coordinate. What I'm going to do is I'm going to put my start coordinate in a really odd spot. I'm going to say my first coordinate position is in LW plus LG plus LW. Now don't forget, these are the variables that the system already recognises. So if I just say build, and then I'm going to zoom that in. So that's what we got. That is going to be the first level point of the dumbbell. Now a few people have told me, oh well, you could do this and do that, but what I'm going to do is cheat. Right click, duplicate. Right, now the beauty is, this point says that it's going to start now over here. Endpoint says it's going to finish here. But what if I change my endpoint? What if I say I want to stay in that position but move upwards? That tells me that I can move that way. Now this would be a single point in space, because obviously they exist in the same coordinate based system. However, if I say TW, which is the thickness of the dumbbell, put it over 2, because I'm only doing half of this, and then if I build that as an example, what we got is our first initial point. It's a slow process, agreed. Once the geometry is there, it makes so much, it makes light of everything. It really does. So I'm going to duplicate again. From now, what we can see is we want to actually move backwards, because we've taken the full length now, but we want to move backwards. And the best way for me to be able to move backwards now is assign this to my beginning point, which is the last position of the former line, and then all I do is I start removing. Build again. So now if I duplicate, now we are now starting at this position. I've duplicated this position, so this is where it sits. So what do we need to do? The next thing now, what we really need to do is we need to start from its last position. So I'm going to remove that to make it match that. Then all I'm saying is I'm going to go inwards. So I'm going to go minus WG and then build. Again, I'm going to duplicate. And within my duplication now, I've got a couple of things. So this now needs to be matched to here, and what I want it to do is move along. So if I want it to move along that position, that tells me that my X coordinate needs to be removed from here, because it's going to move along here but not changing its Y coordinate. So if I build, we're in the same spot again. It's fantastic, love it. So I'm going to duplicate. And it really is this simple from this point. But again, I'm not going to rush with this. So now what I know is I want to move back up. So I'm going to delete that. And my endpoint position, now I actually want to delete this. So you see now starts here and then moves up to here. So if I then build, duplicate again. So you see now it starts to really fall into place exactly what we're doing. So I'm going to remove WG, and I'm going to set X to 0 and then build. And then finally, we need to bring it home. Bring it home. We need to bring it home. So we're going to set our upper point here to 0. And I'm going to set, because it matches here, don't forget. And then I'm going to set my endpoint to sit at 0. So we go like that. And there we go. Now that's our initial endpoint position. Right, so we've got this. We have a representation of what we want to do. So let's go back here. I'm going to right click. What I'm looking for now, oh, I'm on the wrong one, apologies. So I want to go on work plane, by the way. What I'm looking for now is extrude or revolve. Now we're revolving, don't forget. So I'm going to go revolve. Right, now what it does is it says, do you want to revolve around the y-axis that we've given? And you go, well, no, I don't want to do that. So I'm going to go 0 on that. And then he goes, well, you're not revolving around anything now. What's going on? So if I set that to 1. And let me make sure I get everything there. Yep, so I set that to 1 and then I do build. Now what we got is something juicy. We've got something that we can operate with. We've got something that is useful. Now, the other thing that you may not be aware of, and you know, it's nobody will be aware of this. What this has actually done is it's actually created a surface. It's created a 2D. It's created a surface representation of a volumetric piece. What we got to do is we got to say to the system, right, I actually want this to be a solid. So I go back to my geometry. I'm going to go right click. Now I'm sure it was in here. Was it in here? It's in here. Just give me a second. Not union. Oh, conversions. There it is. Right. So within my conversion now, what I'm going to say is I want to convert to a solid. So click that down. Click on the whole thing. And then with it now, if I just say build, look at that. It did nothing. All it's done is it's just put volume on the inside. If there was anything wrong with the part, it would have failed to do the conversion. This is the worst thing with CAD, as some of you will well know. You introduce it and it gives you no real representation of what the hell's just happened. But in essence, it's made it volumetric, so we can now operate like we need to. So I'm going to go build. So it's not a Comsol thing, and this is equivalent to ANSYS and all over the place. So it's just something to be vigilant of and be aware of. Right, so now you'll notice on the notes, I made this from structural steel. No, notice you got the red X here. It's saying, okay, you want a material? There's a domain. This is domain 1, by the way. There's a domain, and it says there's nothing in it. So I'm going to right click. I'm going to go to add a material from library. So click onto here, and I'll just type in. Let's type in steel. You notice on the notes it was structural steel that we're using. So give it a minute. And now it's already recent there because I've been recently playing on some other notes as well. So let's just expand. Let's just bring these down a little bit. Now we've got built-in structural steel. I'm going to right click, add to component. There we go. Excellent. Just what we wanted. So we now got our material. If you do want to question any particular things that's in here, you want to question any particular values, you can chase each piece up and it will give you exactly what's going on. If you find a Poisson's ratio, if you look and go, hang on a minute, Poisson's ratio for structural steel isn't that, you can change it, you can update it, you can do all sorts with it. I love it, I really do. I'm a great advocate for this software, I really am. I do quite like it. So let's move on to the next piece. Now within this, now we've got everything that we need. What we really need to do now is start setting up the environment for what we're going to do. Let's just take a quick look. linear materials. So it's saying, how's it going to calculate the linear materials? You say, well, take it off on Poisson's ratio. If you want to see the equation that's been used for the stationaries, you can see here. We don't actually have much more attached to this, or else there is more things I could show you. There is further details that we can go into with that, and I think it'd be nice to be able to go into that even more. So let's move on to it. Initial conditions, everything's set for a displacement field of 0 because it is sitting in stationary space. So I'm going to right click. Now the first thing I want to do is I want to define how this thing's been fixed. So I'm going to say fix constraint. I want to fix it here, here, here and here. Anybody who's used to MATLAB, you'll know that it has a very close love for pi. So when you look at this geometry, it's actually been created in these types of principles where it's divided by 4 and it's just at each 90 degrees, so it just becomes over pi. That's all that this does it for. There's nothing wrong with it, but that's why it does it. You can combine them, but there's no real need for it. It still does what we need it to. So I'm going to right click. Going to go down to boundary loading. As it sounds, boundary loading, all we're simply doing is saying I want to move it here, 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 here and here. And now it's initially saying in which space do we want to move it in. Do I want to do force per unit area? No, I'm going to go total force because you'll notice my units are in newtons. And for my T out, I'm going to say LF. So you notice now that by using a variable, if anybody's unsure, you can fix the value. But having a variably controlled area is fantastic. So this is case sensitive. So let's do this differently. Let's go LF. See how it's gone orange? Now this is a function I really like. Watch this. If I highlight just over, it says unknown variable. It will tell you what's going wrong. It will tell you things it's spotting, and it will tell you that this isn't right, that isn't right. Fix this, fix that. It's phenomenal. So I'm going to go LF. If I go LF now and highlight, oh come on, are you going to do it? Oh, well, it's gone black, so it's just confirmed that it is accepted into what I needed to do. For our meshing, I'm just going to use a standard tetrahedral mesh that's assigned with this, because if I just go like here, if I go build, that's what we're getting. It's nasty. So for this, I'm going to bring this down. What I would like to do is I do actually want to go through the process of actually building a good, decent mesh. So for this, it's going to be fine, but in a few more tutorials, we'll show you that process. So I've dropped the resolution on the mesh, and it's all right. It's not so bad. It'll be fine. Be fine for what we're doing here. But if we were doing something a lot more sophisticated, then there would be problems. Instantly problems. Right, so we've set it up, we've got us loading, we've got us everything's in position, so let's drop that, and I'll just rename this dumbbell. I'll call it Dogbone because I've named the whole thing Dogbone, so I'll go Dogbone. And right, so we've now got the Dogbone. Oh, excuse me, goodness. Now got the Dogbone, and we're now ready to go to study. I was going to say there's a few functions in here, but I suppose it won't work for this. So what we'll do first is let's just compute. So I'm going to compute, and this should only take a minute or two. Shouldn't take long. I say that should only take a minute or two. And there we go, thank God. I didn't think it was ever going to do anything for us then. So, we've now gone on to here. We've now got this displacement. First things first, I had a comment not too long ago where they said, my God, hasn't it moved? So if I come down, I go to here, and we actually look at the displacement factor. I can change the factor. Now this, basically what it will do is multiply it. So if I click on that, and then go plot, right, and then if I drop this and then say a factor of 2, plot, well you see there, if you see there, so if I go 20, plot, it's a multiplier. Makes it more obvious as to where it's moved, how it's moved. It's not a true representation. You can change it though, you know. You can make it true. Title wise, it's von Miser. Yeah. You can edit this title, but we'll come back to this. There's a few things that we need to do first. We need to establish a bit more detail to this, to be honest. So I'm actually going to do something that everybody goes, ah, can't do that. I can. I'm going to delete it. So I've deleted that because what I actually want is I actually want a volumetric. Close that. What I actually want is a volumetric study. So I'm going to go volume. And within my volumetric study, what I'm actually looking for is, let's have a look. So I'm going to go into here and I'm actually after some principles. So if I can actually find this. I always struggle finding this all the time. I mean, it's got some great tools in here, but I always get myself mixed up as to where. God, I'm getting messages left, right, and centre right now. What's going on? I'm actually looking for principal stresses. Ah, there we go. We've got first principal stress. Right, so let's plot that. Won't actually give us much difference. Right, now we're in a very good position right here. Now you notice here, you know, a lot of the time you look and you go, well, is that 1 or 2 or is it 6 or 7 or what the hell is it? I can't be clear. Welcome to the club. What I'll do on here first though is I'm just going to type first principal stress. Yeah, it's just first principal stress. So it comes onto there, and let's have a look. So we want what we're going to look at. We'll just take the title. Not going to go automatic. I'm going to go custom. So I want something else. So a manual title. So let's call this Dogbone first principal stress, and then we'll plot. Right now, there's a few things we're going to cover with that as well. Outputs, nice plots, things like that. Just because you come away and go, you get screenshots. Screenshots are a bit naff, and when you see them publicised, when you see them put into things, you almost cringe because you're looking at them. I know it's really mundane, but it is quite important to take real pride in what it is that you've done, because you come away and go, yeah, check it out. That is my work, and that's, you know, one of the biggest rewards for anyone who does this type of stuff. Right, now the other thing is we want some maximum and minimums. I have no idea. I don't know about you guys. I have no idea to be sure about what's going on. I know how the stress is moving. Fine. So what I'm going to do is go to more plots. I'll show you this again because I rushed then. So I'll just come over here. So I'm going to go to stress solid. Go to more plots. And what we can do is maximum and minimum volumes. We can do principal surface stress. We'll actually pull that one in a minute. We could do all sorts on this. It is crazy. I love it. So I'll go max and mins just on this because that's only really what I'm after. Now, you'll see here it's actually talking about displacement. And you go, well, we're not after displacement. If you were like me and you get annoyed trying to find these statements by going through all of this, a few things you can do. First thing, I can simply copy that and go across and then type in this and then literally paste it in that way. Second thing, I can either, oh, not that, that's the wrong, that's not going right. So I can either go to my replacement expression, and the last thing that I used was there. It just depends. So I just get really lazy, so I'm going to paste that in. Now what you'll see, it instantly snaps to its default. If you're not happy with Newton meter squared, drop it, move to whatever unit you need to operate in, and that'll give you a better representation. Okay, so let's go plot. Okay, so we're operating here at a max of 2.7. Or we're operating, I'm sure it was 2.5. We're a little bit out, but it's very confident. I mean, the thing is I would say is our mesh is a bit naff for a start. That is a mesh is not a good representation. The concentration's around here. I mean, if we zoom into this particular area, look at the linearization around here. We could tidy that mesh up. I'm confident that that is moving in the right direction. I'm confident that's going to give me something that I can operate with. I'm quite happy with that. But let's say, for example, I come away and go, and then the boss comes down and he says the recess on your inner point there, that's wrong. It needed to be 2 millimeters. So I can go back up to parameters and go, oh, okay. So what I'll do is I'll just drop that, and then just come back. And just for completion, I like to do this, even though it doesn't do much. Build all, and then I will rerun the study again. And there we go. So it's rerun it again in its new state. So if I go to my max and mins, I hate it when it does that. So my max 2.9. Now I would suggest that because of my process that I'm using, it's not giving me the truest of representations. If I close this bar completely, it'll give me a better representation. Perhaps you should be really subtracting on the internal space on the dumbbell, but you can see that we are well within the correct remit of what we were doing, which is fantastic. It's really good. So I'm going to change that back. In fact, no, I'll just leave it like that for the minute. Now the other thing is exporting these. So I'm going to take you through the process with this. So if I just click my image snapshot, what it does, it comes up and says, right, how do you want to export it? So I can export it as a file. It'll tell me where I want to put it, so I'm not going to put it there because that's something else I'm working on. So I'm going to go Dogbone, and then click OK, and then OK. Now there's a few things I wanted to show you, so let me see if we can just snap that out. Click onto Dogbone. And you see there, look at the sizes, look at the font. That is a bit naff, isn't it? So what we'll do is we'll come back, and then I'm going to go up to Dogbone, up to here, sorry. This is right at the top under Utilities, and if I just scroll down, we've got font, default family. So I'm quite partial to Times. So I've got Times New Roman, and then I'm going to come down to my principal, and what I'll do again is go snapshot. Notice here I'm at 12 as a size. Let's just drop that down. Let's go 11, and then let's output it. Let's do it. Okay, so let's close that. Let's bring that round and then open that up. Now it's starting to look a bit more attractive. It's a little bit big for me still, But if I come back again, and now what I'll do is, let's just drop it down to something sensible. I'll go 9, something like that, something small, and it's just because I'm overwriting. So now, reload it just to be sure. Now, for me, that looks really good. That looks really good. That's what I've been looking for. I mean, arguably you may want to rotate the actual geometry, but that now will go nicely into a write-up, into anything. It gives a nice, clear legend to let us know. Gives me the units that you're operating to, gives me some max and minimums to tell me where everything's sitting, shows that the distribution loads, the stress. It's just a nice overall plot. So that is just something for you guys to keep in mind. As a piece of software though, again, I do quite like this. So, right, there is one last thing I want to show you. And we might as well, just for fun. So let's say, for example, that we're talking about that recess. Let's say we want to know the variation of the recess. We want to know the recess when it's under 1 millimeter, or let's say 0.5 millimeters. No, we won't make it too much. We want to see the variation when it's under 1 millimeter, 1.5 millimeters, 2 and 2.5. 4 variations. You have a particular option within this. You can either sit there and go through each one by one and keep running, or you can self-contain these all in one hit. Now this is typically known as parametric sweeps or parametric studies, where it's a process. It'll follow through each individual time and it will give you the result of each one. So you've got to remember as well, I'm actually sat at my PC now waving my arms. I must look like a lunatic. So you'll see on here I've got study. I'm going to right click. See how we've got parametric? Click onto parametric. And come up to here. So now we're on parametric. It's parametric sweep, typical types. We've got all combinations here. So what I'm going to do is I'm just going to do a simple sweep. So I'm going to go, what are we looking at? Now we agreed, if you remember, weight, width, I've chosen such bad names. Such bad names. So if I sweep back, WG was my 2, yes? So come back. Right. Let's change you to millimeters. So I'm going to go 1, 2, 1, 1.5, 2, 2.5. Okay. So now we've got the 4 variations that are there, and if we now click, while solving, plot stress, and let's hit compute. Oh. And now we wait. In fact, I may pause this, guys, for a minute just whilst this solves. And we're back. So, you'll notice I paused it just to save time, to be fair. Right, so what do we got? We've got some really cool stuff. So what we've got is the first study. Now this was the first initial study that we did. And the second one here is very cool. This is now the parametric sweep that we did. Now you'll notice here we've got parametric for millimeters, and if I've got a variation here. So how did it look with 1 millimeter variation? So I'm going to click plot. That's the process that it looked. So what about 2.5 recess, which is quite thin in comparison? That's how it looked. Oh, goodness gracious me. Apologies. Right. So now what we can do is to look a little bit further as to what's going on. I'd like to see a plot which would be able to look at the line, if you will, of separation all the way down and show me what stress is going on. So I'm going to go right click and I'm going to go line plot. From my line plot, what I'll do is I'm going to use parametric study, and this is cool, check this out. All. Now what it says is, okay, fine, how are you going to apply it? So I'm going to right click again, I'm going to go, I want a line graph. Then what it does, it goes on the inside, and it says, okay, if you're doing a line graph, what line are you interested in looking at? Now in my case here, because I'm going from back to front, I'm going to go, come on you swine, there you go, line, to line, to line, and really draw that profile completely along. And then I'm going to go plot. Look at that. This now is plotting the stresses that are occurring on all four. Apologies, not the stresses. That is displacement. Very awkward. Oh yes, that's because in here we've got displacement. If I drop that and then say, I've got to find it again. So I go stress, come down to stress, principal stresses. We're going first principal stress, and then let's plot. That's more like what I was looking for. You see there we have a larger spike under, oh, with no legend. That's awkward. We need to add a legend. So I'm going to go up here, show legend. There you go. So you can see there with a recess of 2.5 millimeters, we spike drastically. And obviously, as ever, it increments. But whatever your particular stresses are that you need to operate in between, this allows you to do that. But you'll also see there that between left and right, the right side is to where, let me just check. So let me just check where we took these from. So that's where we've taken them from. I'm just making sure I'm moving on the right coordinates. So if I go where my fixed constraint is, right, yes. So what you'll see here is where it's fixed, comes in, we've got this huge resistance upon it, and the force is dragging it this way. So it's purely at this point. So the force drags, and then it will concentrate higher to the left side as opposed to the right. You'll also notice as well that the elastication of the material does extend dependent on that recess. So that recess in itself does so much to the actual system. Let's just zoom in a little bit and take a little further look around. You'll see this response as well. Now this is where it's going to come down to I'm just trying to think of the best way to describe that. This is where it comes down to the meshing that's within it, and also the process time that we've used to do it. There is a few ways that we could do this. We could use a range process, which I would like to introduce a little bit further down the line. And also there's a few other things we can do as well. But what I think that does is I think that tidies up quite nicely what we've just done here, which is to do a basic standard test. Then we've done a parametric sweep, looking at the whole thing in each variation, looking at it with a smaller recess through to a larger recess, and looking at how the variation occurs and how the stress has really happened dependent on that recess. Also within here we've operated purely by variables. Nice. We've also looked at outputting. How can we output with a particular format? I like particular formats, like it to be a certain way. As I said, I'm quite partial to times, and yeah, so I think that's a nice overall, if you will. Right. The other thing is, if you come up to utilities, now what it looks for here is you can give it a bit of a description. You can tell it in particular give it a rough overview of to what the actual simulation is about. You can actually choose color themes for the whole system. So if I went dark, and then let me go down here, come to here, and I'll come to here, and I'll see if I can should output darker when we go to export it. So it's really aesthetics. That's all it is. When it comes to here, this I quite like. So if I go to set graphics, now I'm going to go to dark here, and then come up to my utilities. Now you see there it says set graphic window, so I'm just going to go there. I just want to make it look a little bit lovely. So I'm going to come onto here, possibly put it something like that, zoom it in slightly, and then we're going to do set from graphics window. And there we go. So now, when I hit save, that is what you get. If I want to give this out to anybody, I can do. All I can do is I can set a password so nobody can edit it. You can just take a look around it, and yeah, it's a nice little bit of kit. I really do like it. So if you hit save, that's the first initial Dogbone simulation complete. I hope you found this useful, and I hope you've had a bit further insight to Comsol, and it's phenomenal bit of kit and what it can offer. If there are any questions, please either come and find me, send me an email, send me a message, anything you like. I can try and help you. And if there is further reading that you want, there is lots and lots of support networks on Comsol online. There's lots of examples. I would welcome you to take a look at them, see what you think. Okay? So I'll speak to you all soon, if not in the classroom.